Chapter 12, Gravitation, Samples. Sample 1. A particle of mass m1, 0.67 kilogram, is located at distance d, 20 centimeter from one end of a uniform rod, length L 3.0 meter, and mass m 5.0 kilogram. What is the magnitude of the gravitational force F1 on the particle due to the rod? Now, we look at this. This rod, a different part of the rod, has a different distance from the particle, M1. So, even they have the same mass, but the gravitational force will be different because distance is different. So what we do, we divide this rod, uniform rod, in many small sections. Each is about a dr. And we find a dr which can represent every dr, every section. We look at this one. We take this as 0, and the distance, this section to the particle M1 is r. When r equal to d, this is this section, okay? And they can move this one until this section. This section is r equal to d plus l. You get a section. So when r changes from d to d plus l, it can cover every section of this rod. Now, let's see what the gravitational force acting on this M1 by this section dr. Now, according to Newton's law, okay, that's dF equal to G M1 dm, this section, over r squared. We have to relate the dm with this dr because different dr will have different dm. The dm equal to its density times dr. And then what density? Density is the total mass is m. The total length is l. So m over l is the linear density of mass, right? So the dm equal to rho dr, m over l dr. We put dr here. So we get a df equal to g m1 m over l r squared dr. And then we do the integration. From where to where? We see this r is from d here, d plus l. So the integration is d to d plus l. This is a very easy integration, so we can find this one, okay? We take all constant out, okay? And integration only r squared, one. It's very easy one, we can get the r, okay? This is GMRC. In this case, you can not use the center of the gravity to do the extraction. You have to do the integration. We put all number inside, we get a number, okay? Very small, 10 to the minus 10 Newton. Sample. Several planets, Jupiter, Saturn, Uranus, possess nearly circular surrounding rings, perhaps composed of material that fail to form a satellite. In addition, many galaxies contain ring-like structures. Consider a homogeneous ring of mass big M and radius big R. What graduation or attraction does it exert on a particle of mass m located on its central axis at distance x from the ring center? B. Suppose the particle falls from rest as a result of attraction of the ring matters. Find an expression for the speed with which passes through the center of the ring. Okay, let me see this one. We from the basic theory. We take a small section on the ring called the ds. 那么 ds attract this m, okay, we call it df. This is a df along this straight line, okay. What is df? This df is, according to Newton's law, equal to g m, the mass of this ds, dm, over distance r. And we know r squared equal to x squared plus big R squared, right? So we put ones inside. This is r squared plus 3d. What is the dm? Well, the dm is the mass of this ds. Then we look up. If the length is ds, the total ring is 2 pi big R. And total mass m. So you m divided total ring length, this is called the linear density of mass. And we time the length ds, so this is the dm related to ds. Okay. Now, we know that one. The resultant force must be along the central axis by symmetry reason. Okay, so we will see for the total F equal to fx. This x is towards the round, so this minus sign. The I is the positive direction along x. Minus I is go this direction, right? And so they call it fx. Suppose this angle is alpha. We know cosine alpha is x over r, right? Yeah. So this force fx equal to df times cosine alpha, okay? And the cosine alpha equal to x over r. X, this r equal to r squared plus x squared square root. Now total F is integration of total phi's, okay? This one. And the direction is minus r, okay? Then we do it, we put a number inside. Everything inside. df, this one. Cosine alpha, this one, okay? Then we put everything, you counted. This r squared over plus x squared. R squared plus x squared square root, we get r squared plus x squared 3 over 2 to the power. This is x as integration. We look at this integration, looks like very complicated. Actually, if you look carefully, the integration is respect to s. It's nothing to do with this, okay? Okay, so this x and this one are all constant. We take it out. And the integration is just integration ds, we get a 2 pi r. Then these 2 pi r cancel these 2 pi r, we get minus g in m x over r squared over the c. And we see that x, oh, this is cosine theta. So we rewrite this one as minus r g m. This is r squared. This is r squared, okay? R squared, this one. Plus x over this cosine theta. And this is very important answer. We're going to use it later, okay? Question B, the speed. We see that the kinetic energy change equal to the work done by the gravitational force, okay? And we see this force then is equal to F times dr. Actually, this F dr is along x, okay? So the F is this one, fx, we just sketched. The dr is along idx. This is negative. This is dr all along this one, okay? Integration from where to where? From x0 to 0, okay? x0 to 0, okay? This is x dx, gm, big M, this is 3 over 2 power, okay? And this is very easy to do. We take every constant outside, we have this integration. This integration is easier to do. You put this equal to half x squared and put r squared. Finally, we get integration, it's the blue one. 1 over r squared plus x squared half square root. We put the limit inside, and we get this one. And once we know the W and the C, we find a V. Okay, V equal to 2W over M square root. Okay. We have another way to do it. Look at this one. Okay. We look at this ds. It has a potential here. Okay. This potential is gravitational potential minus Gm. This is dm. This is r. Okay. And the whole ring is around this one. Okay. And we can get this m over g because everything's symmetry. Okay. We just put the dm replaced by m. Okay. And we see this r is square root big R squared over here. Okay. Because of symmetry reason, this f is along this direction. So how we find from u, we learned before, this fx equal to minus rho u rho x. Fx divided rho is x. We do this one to differentiation with respect to time tx. We find this one equal to, very easy, minus minus, and to the derivative we have another minus. Okay, we get this answer. This is minus half. We do the derivative minus 3 to this one, and the 2x cancel 2, you get this one. Okay. Now this one is exactly equal to the same thing we deduced before. This r square is big R square plus square, and we have x to x squared is cosine alpha. We use the mechanical energy conservation to solve this question. We know in this case, delta K plus delta U equal to 0, mechanical energy conserved. What are delta X? At this, we have kinetic energy half mv squared. V is what I want to find. At the beginning, it's at rest, so 0. Delta U, the final use is x equal to 0 here. And initially, it's x equal to x0, okay? Then we put the number inside. This one, what is it? This one is GMXC, this one. What is this one? This one is GMG. What is this one? Okay, potential energy, okay? So instantly we can find the V, the same V as we get before. Sample. This sample we prove a part of a shear theory. A point particle M with mass M put outside the spherical shear, uniform spherical outside. We want to prove it. The gravitational force acting on the M by this spherical shear equivalent to, we put all mass at the center of this shear. For symmetry reason, okay, we take the ring. We divide this shear into many rings, and we find each ring acting on this one, the force. And when we put them together, why? Well, because we connect the center into its mass. This is symmetry. Now this ring a different size. Okay. Now what we do is we take this angle. This is ring N. This is R central of 6. This angle theta, sin theta. Now we find a different theta. It corresponds a different ring. Theta equal to 0 in this ring. Secant equal to theta in this ring. Theta equal to 90 degree, half pi is the big ring, and then it goes small. Theta can go from 0 to pi to 180, which is different ring. Okay. Now, let's find a typical ring, the gravitational force acting on this one. For example, this is a theta. Okay, this is a ring. This ring has a width, delta theta. So this angle is r delta theta, this line, the thickness, okay? Thickness h, okay? The width is r delta theta. How about its circular length? 2 pi r. What is the r? It's r related to theta. This is r. This r equal to r sine theta. So the dm, let me see what a dm. dm equal to density times its volume, dv. What is dv? It's density dv. What is dv? dv equal to, around it, the circle, 2 pi r sine theta. The width r d theta, and the thickness h. So this is dv. And density is total mass divided by its volume. This is the volume density. This is their volume. So this is the dm. We look at this one. What is v? V is the shear. The shear surface is 4 pi r squared. Thickness is h, right? So we look at this one. This v is surface area 4 pi r squared multiplied by the thickness is the v. So m over v is the rho. This is its dv, and then we cancel out something. Finally, we get the mass of this ring is half total mass sine theta d theta. It relates to where it is theta. Different theta, you have different dm. Also depends on the d theta. The d theta larger, the width is larger, it's very large. So remember, there's a dm. Now we review. We use the result of previous sample. The ring acting on this one, the gravitation force is equal to, this is a minus gmm r squared cosine alpha. This is alpha. R is the distance from here to here. This is r, remember, okay? This m is the total mass of the ring. We are going to use this one. It's along this central force. Okay? Now, then we see this ring. This ring, we know dm. The force, we take this one. Symmetry reason. This df equal to gm dm. This is here, we call it s squared, an equivalent to r squared in previous case. Cosine alpha, this one. Okay? Yeah. dm, what is? We just calculate dm is half m sine theta d theta for this ring. So we put this one inside. This is what it means. This is this ring. This ring located at angle theta. Okay? And then the gravitation force acting on this m is df. Okay. Then what is the total force? We put all different ring acting here. Then it means sigma. That means integration. So we do the integration of this one. Gm half over s squared big M sine theta d theta cosine alpha. From where to where? This theta, we're starting from this ring. Theta equal to 0. And then big, up to big, smaller, sort of here. Up to theta equal to pi. So integration theta is 0 to pi. Then we cover whole the ship. Okay? Now, next we do the integration. D theta, the theta is from 0 to pi. The question is, when theta changes, S changes. When theta changes, alpha changes, cosine alpha changes. So you cannot do it. What we do, we want to find the relationship. What is the relationship? We see the S and theta. This is S. In this triangle, we have a cosine law. S squared equal to big R squared, small r squared, and that minus 2RR cosine theta. This is the cosine law of this angle. And with this one, we do the derivative on both sides. We get a 2s ds. This is 0, this 0 is minus 2RR. Cosine derivative is minus sine theta d theta. 2 minus get a positive. And we find sine theta d theta equal to S ds over R. Yeah. Now look at cosine alpha. We have the same triangle. Cosine alpha equal to big R squared equal to S squared plus R squared minus 2SR cosine alpha. Another cosine law. So cosine alpha equal to R squared plus sine S squared minus big R squared over 2RS. We put the cosine alpha in, sine theta d theta in, we get F. F equal to 2GMM taken out. Integration, this cosine alpha equal to R squared plus S squared minus R squared over 2IR. Sine theta d theta equal to S ds over AR. That's it. Now we do the integration to S. When we take this ring from here, big to here, what happened for S? This S is from this S. Small r minus big R. Up to here, small r plus big R. So the integration here is small r minus big R to small r plus big R. That's the integration we want to find. And this integration is not too difficult. We cancel out this S. We take these 2R squared R out. And we get this one. Comes out. Inside we had a square get 1. Okay? And R squared minus over S squared dr. This integration is very simple one. And the integration is from here, S. So from here, S equal to small r minus big R. Up to this S is small r plus big R. It's very easy integration. I'm not going to do it. We get the result. This result, what? This result means the gravitation force from this uniform shear, a sphere shear, is equal to what? We concentrate all the mass of shear at the center. This 2 point, big R, this small r, R squared, G, small m, big M. That's the first part of shear theory of Newton. We prove it.